The second part of the experiment, once we collected the citral and the aqueous mixture, so this is what was in the receiving flask. I just carried it over to this particular fume hood. And what we want to do is to extract the citral from the aqueous layer. It's such a small layer that it would be hard to try to pipette that layer off. And what we can do is to add another organic substance to that mixture, of which the citral would be soluble in. And the substance that we're going to be using to do that is ether, diethyl ether. So when you do extractions, typically we use this piece of glassware that's referred to as a separatory funnel. We always have a stopper, and you always want to use these ground glass joints, again, these stoppers that are specially made for this. I went ahead and put some grease here. Once I poured the materials in here, I will put this in and then rotate it because I want that good seal to form as well. Before I do that, just a couple of things of using the separatory funnel. Before you ever use it, you want to make sure that the stopcock is perpendicular to the separatory funnel. That means there's an opening here that will allow whatever you pour in here to go straight through. And when it is perpendicular, that hole is being obstructed, so you can't have anything to leak through. The other thing I should mention too is that when you rotate the stopcock, you don't want it so tight that it's so terribly difficult to move, but you don't want it loose either. So we have a bolt type clip here at the end that we can rotate to tighten it or loosen it whenever we need to. So just make sure that when you use a separatory funnel, this stopcock is always perpendicular to the separatory funnel itself. Now I'm going to have two flasks. I've labeled one A for aqueous, and then I've labeled the other one E for the ether layer. Remember, what the ether layer will contain is not only the ether, but also the citral that will dissolve in it. And then what I'm going to do is to measure out about 15 milliliters of the diethyl ether and then pour into that. You may be able to see just a very thin layer, but this is what I was referring to earlier. It would be very difficult to try to separate that with such a small layer. So I'm going to measure out 15, close to 15. And I will say it's not critical if I did 15, if I did 18. It's really not that critical, because at the end I'm going to evaporate all that ether. So if I have more than I need or a little less, it's not a very big detriment. When you use ether, you always want to make sure that you use it under the fume hood. And I have roughly about 15 mils. And I'm going to take this and I'm going to pour that into our separatory funnel. And ether is also one of those substances that you cannot measure out ahead of time because it will evaporate very quickly. I'm going to rotate my stopper. I just want to make sure that the grease is surrounding this. And now you can see the presence of two distinct layers there. And when you do an extraction, you always want to take your separatory funnel and you want to put your finger over the stopper and you shake it a little bit, and then you always vent it. And what happens is that when you vent it, you are, when you swirl the mixture, you're creating pressure inside that container. So if you don't vent it, it's not unlikely when you put it back up here that the stopper will pop off. I've seen that happen before. So I only shook it once. I just want to do it another. And notice it looked like a drop or two, and sometimes that spits out. That's normal. And then I just want to do it one more time just so that you can kind of see. Now, if you notice, we've got two distinct, and I'm going to go ahead and take my stopper out because you can't open the stopcock. Well, you could open it, but nothing will drain unless you take the stopper out. So that has to be removed. And if you're not sure about who is the organic layer or who's the aqueous layer, some students think that the aqueous is always going to be on the bottom. It is in many cases, but not always. We're looking at densities here. Density of ether is much less than that of water, so it makes sense that anything that's dissolved in it should be less dense than water. So my organic layer, i.e. the ether layer, is the top layer. The bottom layer would be the aqueous. You never want to throw anything away when you do an extraction, and it is a good idea to label your flask, and I would always use an Erlenmeyer flask to collect the material, not a beaker. So I'm going to open this up, the stopcock, and what we want to do, and there's a trade-off here. If you notice, I'm letting the aqueous layer drain, and you can see this is gradually moving down. You could do it fast if you wanted to, but I'm just doing it slow mainly for so you can kind of get a better idea of what's happening here. When the layer of the organic gets really close to the stopcock, I'm going to cut it off. Now, I just want to say this also. It is so hard to cut it off exactly where one layer ends and one layer and the next layer begins. So it's possible that I may still have some aqueous here. It may be possible if I let it go a little bit further, I may have a drop or two of the ether layer here with the aqueous layer. And that's okay. That you're always going to lose some material anytime you do some type of separation. So I'm going to move my aqueous layer. I want to wash this twice with the ether, so I'm going to save that. But I got to get rid of the ether that's in here. So notice I've got my flask that says ether. And I'm going to drain all of that out into this Erlenmeyer flask. And always make sure to close your separatory funnel. Now, as I said before, this ether is very volatile. So you don't want to just leave it out in the open. What I like to do is to take some paper towel and just kind of stopper that up. So we'll kind of stopper that up, and I'm just going to set that aside. I'm going to use that again. I'm going to set it in the bag just so I don't knock anything over here. So now what I want to do, I want to take the aqueous layer, and again, it's a good idea to use your funnel. Stopcock is closed, and I'm going to take this aqueous layer and pour it back into the separatory funnel. Now I'm going to measure another 15 mils of the ether. And there was a drop that hit the countertop here, bench top here, but it evaporates almost as fast as it spills. Got about 16 mils in there, which is fine. Now I'm going to take this, pour it back into this is another fresh 15 mils of the ether. And a lot of times when you do extractions, and again, the purpose of an extraction is you're using another organic substance to pull whatever it is that's mixed with the water away from it. We will see a couple labs down the road where we will probably use acid-base chemistry in addition to extractions. We'll do some chemical reactions inside the separatory funnel, but the premise is the same in terms of how you separate the mixture. And remember, and it's not a bad idea to give it just a few seconds for the layers to separate. You can see here very distinct layers. If the aqueous was on the bottom layer in the first washing, it's still going to be on the bottom. There's no question about that. So this is the aqueous layer. The top layer is the organic, which is the ether layer. So I want to drain off the aqueous. And once I drain off the aqueous, I'm really done with the aqueous layer. I'm not going to do anything else with it. But Always do not discard any flask, any fraction from these extractions until the lab is done, because it's very likely, it can happen more often than not, we get confused about what flask contains what, especially if we don't take the time to label it. And if I know that I should get 2 layers and I only have 1, that's a red flag, I've done something wrong. So I'm going to take the stopper off. One other thing about the grease on the stopper, if you put the stopper in without that grease and I turn that separatory funnel upside down, the ether is very likely to seep through around any cracks and crevices of that stopper, and then you'll have a spill on your hands at that point as well. Now I am finished with the aqueous. I'm going to set that aside. I'm going to take my flask that was labeled E for ether, which is what was on top. I'm going to remove my paper towel stopper, and then I'm going to drain all of that into that same flask. Now, anytime we do an extraction that had water in it, which obviously we did when we did the co-distillation, we want to make sure that this ether layer is completely dry. So what we do is we typically put in some type of drying agent that will pick up any moisture, any water that might be in there. And what we're going to use today as the drying agent will be sodium sulfate. It's anhydrous sodium sulfate, which is a white solid. So we're going to use, and it's anhydrate, means it doesn't have any moisture with it. But when I put some of this into this flask, if there is any moisture that's there, it will typically clump up. I usually don't weigh how much sodium sulfate I'm going to add. I just kind of add a little bit, swirl it. If it looks like it's not moving freely, I'll add a little bit more. You don't want to go crazy and cover the whole bottom of the flask necessarily, but it's kind of, you add a little bit, then you wait and see what happens. And if you notice when I swirl it, I'm not sure if you can see that, but it looks like there's some clumps that have formed. So I'm going to add a little bit more to that, because I don't want it, if it's clumping, it's doing its job, but I want to make sure that I've added enough. So I think I've added enough of the sodium sulfate. Now, this we like to kind of let sit for about 10 minutes. So I'm going to let that sit for about 10 minutes. And then the next part of the experiment is I've got to remove the ether, because remember, what is inside the ether, let's say excluding the drying agent that you see here, is the citral. The only thing I want to collect is the citral. So I can't do that yet until this sits about 10 minutes. And then what I'm going to do after that, I'll take a round bottom flask, I'll decant the ether into a pre-weighed flask, round bottom flask, and then I'll evaporate the ether using a hot water bath. So let this sit for about 10 minutes, and then we'll come back and use the hot water bath. What I have here, and I'll remove the pipette, I've pre-weighed this 50 milliliter round bottom flask, and the weight of that flask was 37.988 grams, 37.988 grams. And what I have here, I took another pipette, and I took a small piece of cotton, and with the aid of another pipette, pushed the piece of cotton so that it looks like a filter. And the reason I'm doing that is, if I try to decant the ether layer into this round bottom flask, some of the sodium sulfate is not clumped, it did not clump, and I'm afraid some of that may carry over. So what I want to do, I have another pipette, and I'm going to see if I can transfer, and if any of that solid gets up in the pipette, then it will be caught by this cotton plug. You could do a gravity filtration. It's just that you did that, it could, some of your sample may crystallize too. This doesn't take too terribly long. And just wanted to draw this to your attention also, you don't have to use this only when you're dealing with ether. It's just a good way that you can fairly quickly just keep any small particles from being transferred over to what you're trying to evaporate. Now, the thing about ether is it is a very flammable substance, and we have to be very careful when we use it. So what I have here, I have my flask that has the ether in it and the citral, and I've made sure that it is securely fastened to this clamp. Now what I'm going to do, I have a hot water bath over here, and typically you do not want the water bath to be boiling. It doesn't need to be. So what I'm going to do, I'm going to barely touch the surface of this, and then I'm going to swirl it. Now eventually, and I'm kind of erring on the side of caution because I don't want it to start boiling until the volume of this decreases quite a bit. So you don't want to really be careless in how you slosh it, because you don't want any of the vapors or the ether itself to come in contact with something that's hot. So I'm going to place this on the top, I'm going to remove it, and then I'm going to swirl it. Eventually, when it gets hot enough, then it will start bubbling inside the flask that you'll see later as soon as that happens. But I'm just trying to get this to evaporate a little bit without adding too much heat initially. And ether is one of those substances that has a very fairly low boiling point, so it shouldn't take a lot of time. It will take some time, but it shouldn't take a tremendous amount of time to remove the ether. Probably less time. We could use a simple distillation, but if you kind of think about how long it takes to set that up, we may get it evaporated here before we finish setting up the apparatus. So again, this is just going to be a little bit of tedious, but you just want to err on the side of caution here with the ether. And the reason I'm swirling it too is because, you know, we've talked about this before, that if you heat something that doesn't have a boiling chip or a stir bar or something like that in there, you know, there's nothing that will keep that from jumping out of there like a geyser. So we just want to be careful. Ether is one of those things that you can't be too careful with. And if you look closely, and you may not be able to see it, but sometimes you may just be able to see the vapors of the ether. It's evaporating on its own as well. It certainly takes longer than if we're putting it, although I just saw a couple of bubbles there. That may not be from mixing. And the liquid that you see on here on the top of the beach top is just water. Nothing is splashing out. I'm trying to take care of that, none of that to happen. When most of the liquid, the solvent ether has been removed, then I can let it sit in here a little bit longer. Volume decreases, I may leave it in a little bit longer. But when it's initially half full, I want to take my time and evaporate it pretty slowly. I think we're getting close to having most of the ether removed. I'm just going to let it sit in here a little bit. I don't really notice many fumes coming out the top. I don't really see that at the round bottom flask. And if it looks like the volume isn't changing much, that's usually indication that the ether has disappeared, because this doesn't boil until 229. So certainly we're not going to be that high to lose any of our citral. I don't see any more bubble formation. I'm not noticing really a difference in the volume.
I don't.
I'm going to let it sit there one more time, and then I'm going to take it out and I'm going to let it cool, and then I'm going to weigh it. And then after I weigh it, we want to do a couple of chemical tests that let us know if we've got a carbon-carbon double bond, or if we have an aldehyde group, because both of those functional groups are present within the citral. It doesn't mean that we've isolated it completely pure, it just means we've isolated it. So I think that is done in terms of removing the ether. So I need to let this cool, and then I'm going to weigh it, and then we'll do the chemical test. Okay, just to show again, this is the amount of material that we collected from the extraction after evaporating off all the ether. And the the round bottom flask with these contents in it weighed 39.303 grams. And what you will need to do is to find out gram-wise how much of the citral we collected, and then find the percent recovery by taking that and dividing by how much of the lemongrass oil we started with. The next thing we need to do is a couple of chemical tests. Chemical tests are great ways to recognize whether or not we have the presence or absence of functional groups. In the citral, we should have an aldehyde group, and we should also have 2 carbon-carbon double bonds. The reagents I'm going to use to test for the presence of those groups, I'm going to use chromic acid to test for the presence of the aldehyde group. Chromic acid is a good oxidizer, and if an aldehyde is present, it will react with the chromic acid to form a carboxylic acid. So the carboxylic acid, if that happens, then the color change, we should see a color change of the chromic acid. The potassium permanganate solution is useful to detect the presence of carbon-carbon double bonds. What I'm going to do is to show you what these reagents look like where nothing has reacted, and then we'll take a look at after a reaction has happened. I'm using acetone as a solvent for each of these tests. Chromic acid, this is what we would call the control, has that kind of orange color. Nothing's been added other than the chromic acid and the solvent. So what I'm going to do now is to take a few drops of our product, our citral, and then I'm going to add, just kind of swirl that to make sure it's dissolved, and then I'm going to add a drop or 2 of the chromic acid. And you right away can tell that there has been some type of reaction that has taken place. If you compare it to what it looked like beforehand, notice that the orange color has disappeared. If we let this sit long enough, typically we end up with something that looks more like a blue-green precipitate. I'm going to add a little bit more acetone to that, just to give a little bit more volume. Yes. It almost looks like there is some type of precipitate cloudiness that has formed. Kind of hard to tell the exact same color, but we have noticed a color change. Notice if there was no aldehyde group present, it would look like this, but we do see that change. We did form a precipitate. So we would say, yes, we did have the presence of the aldehyde group. So what I'm going to do next is test for the presence of the carbon-carbon double bond. So remember, I've got acetone into each of these. I'm going to have a control where I add 1 or 2 drops of potassium permanganate to the acetone solution. And this is what potassium permanganate looks like in acetone. It has that nice kind of purple color. To my acetone mixture or solvent, I'm going to add a couple drops of my citral that we collected, and then I will add a drop or 2 of the potassium permanganate to that. And I think we can tell that something has changed. Typically the purple color will disappear and we end up forming more of a brown precipitate. I think you can see the difference between those two if I kind of hold them side by side. So this is the control, has that purple color. You can see that the purple color has disappeared and we form more of a brown precipitate. So what does that tell me? That means we did isolate something that has a carbon-carbon double bond. I want to go back to this one because this is looking more of a kind of an olive green to me in terms of the solid. So sometimes it takes a few minutes for that to happen. But again, chemical tests, we have the aldehyde group. We also have the carbon-carbon double bond.